Welcome back, everybody, to E340 542. It's our 8th lecture. That means halfway through the semester, which is hard to believe. Time has passed very quickly, at least for me. We're going to be talking today about a little bit final discussion of epidemiological models, a lot of which was already done in the homework, so we may go through it relatively quickly. And I want to get through the beginning of discussing in-host models of viral infection and immune response. We're a little bit desynchronized. We got a little bit desynchronized between the homework and the lectures. And so several of the problems that were in that previous homework will probably make more sense once we do the introduction to in-host models, because they were really written around that. So the other thing I need to remind you about is that this is live streamed on YouTube and recorded. So please remember that. So today we're going to do our in-class review, and I think Drew says that he's ready to present. Does anybody else want to present today? If you do, we could do 2 people probably today. If not, we'll have Drew do it, and then we'll do the rest in subsequent weeks. And then we'll do a little bit about other kinds of epidemiological models. Again, we did a vaccine model already as a homework problem, so, and a little bit in class, and so these won't be unfamiliar to you. And Giuliano's shared code, people seem to find a little challenging the idea of trying to determine the frequency of oscillation of the waves of an epidemic, and Giuliano shared some code on that. And then we'll jump into in-host replication models. We're going to find that the in-host models start out looking just like SIR models for epidemics. You can't get away from them. And then we'll see how far we get with that today. So I guess to begin with, why don't we just start out by having Drew present. Thank you for jumping in and being willing to do that. And I do this, turn the screen share over to you, Drew.
Sounds good. That's weird. Does this look, is this screen sharing correctly?
Yes.
Okay.
That looks fine.
All right. So the model I took a look at from last year was COVID-19 BSV IRD model. So basically the model is sort of like the SVIR models that we did in the homeworks, but it incorporates birth and death. And so there's one pathway for birth that leads to susceptible, but there's multiple pathways for death. And anyway, also it's a Jupyter notebook on NanoPub and has some interactive stuff that you can do. So one of my main things I noticed about it is that the model, well, the project doesn't really ask and answer questions. It doesn't really draw any conclusions. It's more figures of a model itself. So I think these are basically the questions we'd be looking at. And so it has figures of like the natural deaths pathway versus the deaths from the infection. And it also just has an overall population versus time. And then it plots the model and also R naught. And there's also another section where it explores different vaccination pathways. And so the first vaccination pathway is just as if it's one shot and then you're vaccinated, and it has a certain like rate that it works. And so it explores the prevented deaths for that. And then also it does a double vaccination model where you have to get 2 shots, and after the first shot, it works at like half capacity or whatever. And so I'll go ahead and show it so we can look at the equations that it uses. Here we go. So yeah, here's the birth pathway, and there's several ways several ways you can die in this model, but the main thing is it is basically just an SVIR model, just like the ones we worked with. But yeah, this time we have death, and it's kind of important in this model because, for one, now if you die from the virus, you're not becoming susceptible again and reinfecting people, and also you can measure the deaths in the figures that we're going to look at. I think okay, no. All right, so here's the time versus deaths, and like I said, it's interactive, but the defaults seem to be realistic. I think he used information from the CDC and stuff. But so this blue line is like the natural death pathway, and it's linear because everyone just dies at a certain rate naturally. But you can see that there's an initial spike from the initial infection as it spreads to the population, and then it sort of settles out. And then we can see the total population, and it looks like a huge drop, but it's only because it's going down to this number here. But it uses, I think the initial population is based on like U.S. population, like 300 million or whatever. So I think these are in thousands or whatever that is. But yeah, that's sort of a plot. But again, it's not really drawing a lot of conclusions with these figures. It's sort of showing stuff. But again, since it's like an SVIR model and it's plotting SVIR here, it actually looks similar to the graphs that we saw, I think, on homework 4 or 5. I think what's also interesting is this R naught graph. I don't think we've plotted that before. Prevented deaths. Yeah. Okay. So this is the graph that sort of compares like the vaccination like pathway. So I think it's the original just model versus including vaccination. And the only thing it's hard to see because it's these numbers are so big that it's hard to see the difference between the two. But you can see that the altered pathway is below the original, and then it says death prevented down here. But so this number is at like 40,000, and we'll see on the double vaccination model a different number.
So in that
Again,
one, what happens if you pull that's starting out with a vaccine efficacy of only 10%. So if you pull the vaccine efficacy up,
let's try this. All right, yeah, you can see the difference it makes.
and I guess also you're starting at a year into the epidemic. So if you started sooner, presumably you would have fewer deaths. I don't know if you put the start time to say 180 days, which would be 6 months.
Mm-hmm.
Then maybe you get a little bit more visible difference.
And yeah, we can change some of the other stuff. First, I'm gonna let's see. There's the SVIR model for that. But yeah, in the double vaccination, they do ask the question of an interesting question of like if you could just vaccinate, everyone with like one dose, and then give certain people that need it 2 doses. And so that's what this model's sort of supposed to look at. This one down here. There we go. So now you've got a fractional efficacy of like 50% that the vaccine works at with just 1 dose. But I guess the conclusion of that question would be no, because you end up with a lower deaths prevented with the same numbers. But yeah, you can change how much the first dose works. And again, how the vaccine works in general and when it starts. But generally, the sooner you start vaccinating people, and the more that are vaccinated, obviously, you get a bigger deaths prevented. Although for some reason, I've skewed these numbers somehow that it's going in the negatives. I don't know what's going on there. But anyway, that's generally the model, but we can look at some of the other figures and change some of the stuff if you want. But
So what was your take of this from this? What's your takeaway on this application?
I think the main takeaway, besides like the basic charts that it shows of the general COVID model, is it's sort of, I think the most interesting figure is the double vaccination stuff, because it was asking a sort of question of how much you need to vaccinate people in general if you can just give people one shot. But using the defaults that it comes with, you can see that it's kind of a no answer. But I think the main critique I have of this is that it doesn't come to a lot of conclusions or have explanations for the models. But it is still interesting to see.
So if you were going to make a single change, if you were reviewing this or grading this, and you were going to go back to the student or person who wrote it and say what needs to be changed, what would the single highest priority change be?
I think my highest priority, if this were my model, I would try adding more just really explanations. I think the models and figures are fine. I would I don't know, I would just next to each figure have some sort of question that the model's trying to solve. And then I would have like an explanation on what conclusion I come to based on my own things, but also still letting the user interact with the model themselves.
I mean, I guess one thing I noticed when you're showing it is there are no exercises. It doesn't say change this, try this. One thing you can do, and it's a little more work in the Nano Hub, is you can have what are called resources, which are not the simulation itself, but basically are supplemental materials. So you could design your application to be more like this, where it's got just the simulations, and then have a separate file which had try this, do this, and so on, not have it in line. But I noticed that there doesn't seem to be doesn't say if you change try changing this or any of these kinds of things. Doesn't effectively give much instruction about how to use the model. Are there any other things that you think could be improved or would be helpful if you were going to approach this for the first time, which presumably you did?
Yeah, I think that is a good point. Is that it does give you these widgets to interact with, but the defaults that they're set to, I think, are based on like U.S. data on like COVID stuff. So the point of the widgets, I guess, is so that you could change it for other countries and stuff. So maybe adding like sort of defaults, more defaults that you could switch to for other countries, or even, just a place where you could look again, like I guess like exercises, telling someone what things they would be changing, because yeah, it's hard to say. But also the default for the vaccine thing is set pretty low. You're right.
That one didn't seem to work, did it?
Oh, no, I don't
Oh,
think it
I
does.
know, because effort is set to
Oh.
0.
Okay. Yeah, there it changes a little bit. It's a very minor difference.
So not a big change. It's a bit hard to believe, but of course, there was a period when there wasn't enough vaccine available. And so there were countries like England and Mongolia and Nepal decided that they would vaccinate everyone with 1 shot before they did the 2nd shot. Whereas the US, they did the 2 shots from the beginning. Israel, they did the 2 shots from the beginning. There was a fair amount of debate about which of those approaches was preferable. So that was, I think, the motivation there. Maybe that wasn't explained. I don't know if that was explained clearly in the application or not.
Yeah. Well, they did sort of ask the question of whether or not you can reach immunity or not, but they didn't really come to a conclusion on the question. I don't think. But yeah, that is sort of the point of this model, is to see that with the double vaccination. But yeah, it's sort of up to the user to reach that conclusion.
Yeah, it looks like having some historical background about why that's an interesting question would be helpful to motivate it. In fact, it looks like maybe the British were right in the sense that a longer interval between the 1st and 2nd doses may actually have been more effective. But there was a question where if you have a large number of people with a single shot, they're certainly more susceptible than people with 2 shots. And so it's not obvious whether you were better off having a quarter of your population double vaccinated or half of the population single vaccinated, for example. And so maybe that kind of question could be framed more specifically, and then that could be tested with those sliders. So those are some of the things one might want to think about. I'm sure there are more. Are there other questions from the people in the room? The whole point of this exercise is to help you think about designing your own projects. Did it give you, Drew, did it give you any insights into what you want to do when you're presenting the material you're going to be presenting?
Yeah, I think so, because it's pretty similar. Because my project, it's not an infection model, but it's like a sort of like cyclic model of like chemical pathways and stuff. So I'm going to be plotting charts just like this, and also having sliders and stuff. But yeah, I think this is generally the sort of thing I want to go for. But yeah, I think what you said about having a way to present without having all this stuff in line would be cool to see.
Oh, so that's something that maybe is a setting issue in the application. If you click on where it says app mode, that will show it the way a user is supposed to see it. It was set up so that it didn't
Oh, there we go.
that hides the Python. So it looks more like a textbook. Okay, any questions, comments? I'd like it. I mean, at least one person I'd like to ask a question. because I think it's important that you all, this is an exercise you're all going to do, and it's important. Drew was great. It was brave in going first, and so maybe seeing what he presented, you can ask, are there things that he could have considered that you think were important, or questions about the application that he didn't cover or could cover better, or or comments about the application when you see it in action that you think could be improved?
Yeah, while it wasn't in app mode, while it was in the other mode, um, being able to see all of the uh, all of the like code implementation, um, I thought that there was that was probably a bit too much. Uh, but so I'm wondering in this mode if the actual mechanics of the thing are well explained enough.
Yeah, actually, I kind of agree with that because actually, I noticed that they kept the equations sort of here that are like the tellurium sort of way to have it in there, but I think having like the actual like mathematical way written out uh, would be kind of nice to see. That you could more presentable than having it written in code form.
That's a good point. I suspect what happened there was that somebody ran out of time when they were putting the app together. That's one reason. Those are good, all very good observations. I mean, this is one reason why I'd like people to try to get the at least preliminary versions of their apps done early enough, because actually this kind of polishing is not trivial. It takes time to do it. The writing the simulation takes time, and then writing the text around it takes time, but actually getting it to work well in a way that somebody else can learn from is a lot of effort. And so I think those are all excellent observations. Yes. Well, we talked about events last week, and you can see there's that event in that under important parameters for equations, down a little bit lower. That was the continuous assignment, the colon equals, and then a little lower at time greater than start time. There's a change. So it's definitely using some of the things we covered last week. If you go back to the edit app mode for a second, up in the top right, we haven't covered yet how to do the user controls, but you can see in one of these blocks how you put the user controlled sliders into the simulation. Again, this is interrupt based or event based programming, and so it has the function. It's actually a little bit like what Josh showed you for the optimizers, where you fundamentally write a function that does the updating. This interact function is quite convenient. It helps. It's a pretty simple way of doing things. It winds up with the sliders that, if you're doing very simple sliders, it's quite simple. If you want to do more complicated, fancier formatting, then it can get quite elaborate. And so there's sometimes a little bit of a tension in terms of you want to label the slider in a particular way. If you go outside of the range of the defaults, it winds up being a little bit problematic. But it's something to play with. And so I encourage you, when you're developing your own applications, to look at how the interactivity is implemented in these examples that were done last year. And definitely feel free to say, gee, he in this case, did the sliders in this way and I liked it. And you can template off of that, or vice versa. If there's something you don't like, it gives you something to think about. Okay, other comments, suggestions? Okay. Is there anyone else who would like to present an application or today? Everyone is going to have to do this. So if you do it today or later, you're still going to have to do it. So, but if people need, is anybody else ready? There are a few people who hadn't joined the class when I asked the question last time. No? Yes? Okay, give me 1 second here. I'll be right back. Thank you, Drew. That was great. Appreciate it. Okay, sorry about that. There was some noise I had to stop in the background. Okay, thank you very much for that, Drew. Now I hope that you can look at Drew's presentation and also think for your own presentations about how to respond to that, and we can keep working on this together. So again, we saw events. We just had a review of events in the example that Drew showed. This idea of event name at some kind of logical expression, often involving time, but not necessarily, could involve the level of a variable as well. And then something that is changed, either a parameter value or variable value. And the key concept with an event, less of an issue with time if it's only true, becomes true once, is that the event triggers every time the value of logical expression goes from false to true. And so if you have something that's cyclical, the event will trigger multiple times. And the warning that if you try to have two events modify the same variable or parameter at the same time, only one of those two events will happen, and it's random which one. And that can be a source of confusion. And so you have to be a little bit careful when you're designing multiple events operating on the same variable or parameter to make sure that you don't have them both happen at once. And then we saw this, also this example of continuous time updating. Example here, s colon equals 0.2 plus sine of time. Again, the key point here is that antimony is not a programming language, it's a model specification language. It's turned into a program when you load it with that TE load A, and all those arithmetic and mathematical operations are evaluated only at the beginning when you do the load. And so you have to be a little bit careful. I think somebody had a comment in one of their homeworks that they ran into a situation where they were trying to do a parameter sweep of a parameter like S0, and it wasn't doing anything. And this is why that is the case. you still have sometimes in antimony a little bit of a problem, because if you say S is equal to colon equals 0.2, then S cannot be used in a rate equation as on either side of an arrow. S can be used essentially only as a parameter in a rate equation. And so that means you have to do a little bit more work if you want to have time varying values on top of a rate law. And then we'd mentioned before that you can write ODEs directly using the prime syntax. That's equivalent to writing nothing goes to the value, which is equivalent on the left-hand side. And you have always that choice. If you do write it that way, K2 prime equals some function, you have to specify the initial value of K2. All right. And then I was just going to, I want to skip through this pretty quickly because I want to get to the in-host modeling. But we've seen now a couple of different modifications of SIR epidemics. The most common one that we're going to run into is SEIR. SEIR, and we'll see this actually in the in-host cases as well. SEIR epidemic models have an additional phase, which is called exposed, where you go from susceptible to exposed to infectious to resistant. That exposed phase is the period between the time you have somebody cough on you and the time that there's enough virus in your system that you can infect somebody else. In reality, that time varies a lot depending on the disease, and you can look up values for it. It's not always obvious what the exposed phases does, and in general, it doesn't have a big effect on the way the system behaves. If people are trying to match very good quality data for infection in a population, then that latent phase winds up being pretty important. But you're not going to see big changes in the behavior of the models by adding an exposed phase. So maybe we can try doing that. If people feel like, why don't we try that just as a warm-up? Why don't people grab their SIR model, their basic SIR model, and add to it a exposed phase. And the one thing that you would need to add to that, let's assume our virus has an R0 of 2. Remember how to translate that R0 into N gamma and mu. And imagine that mu is about a 14th of a day, which is equivalent to saying that once you're infected or infectious, it takes about 2 weeks to recover. This is actually rather different from the COVID case, even though the duration of infection with COVID lasts typically about 2 weeks. When you do the SIR models of COVID, you find out that people are typically infectious in the model for about 4 days. And that's because once people get quite sick, they don't go around infecting people. So the duration of the infectious phase is really the period when they're not severely ill. And that's only a couple of days. The actual recovery takes much longer. So it takes about 2 weeks. So why don't people fire up an SIR model, use R0 equal to 2, use mu equal to 1/14, And then we'll have one extra parameter, which is kappa, which is how long does the latent phase last. And you can sweep that between 1/2 and 28th. Probably easier to sweep the reciprocal. So sweep the delay from 2 days to 28 days. And ask the question, what happens when you change that to the number of infected individuals, the maximum number of infected individuals at any given time, the final number of people who are ever infected, and the time at which the maximum infection occurs. Is that clear as an exercise?
So yeah, this is how it looks like. And
So one thing so k equals 10 would mean that your infectious, your latent phase lasts 1/10 of a day,
mhm.
2 hours. And so typically you want your k to be small, be measured in days. So it'd be 1/5 of a day, 1/2 of a day, and so on. So instead, not 2, but 1/2. Okay. So then you're going to have to change the time scale so that you can see what you're getting. All right. And why don't you, that's fine. So why don't you try overlaying on that the value for k equals 1 over, I think we said 1 over 28. So why don't you try that?
Okay.
So you can run that by itself first. You don't have to copy it. No, but I'd like you to plot on the same graph, plot the run when k is equal to 1 over 28 as well as 1/2.
Okay. Yeah.
So that doesn't require changing the antimony code at all. How would you do that?
I'll have to call it from outside twice, right? The SI model.
That's right. So you only have to add about 2 lines of code to the program.
Okay.
You don't need to. How do you change the parameter value in antimony?
M dot. Sorry. This is right.
So you give it the value you want. Okay, that's fine. And
I
then
guess. Yeah, I'll have to reset the values too, right? Something like.
okay, that's a good start. So what you need to do, you mentioned it already.
Yeah, what was the code for that? Like I forgot the code for that. How do you reset the values?
So those are a couple of, I mean, again, those are things that initially you can look up, but those are a couple of, there are not very many things you need to remember. That's one that you probably should be trying to remember. It's m dot reset all.
Okay.
Camel case. Actually, not the reset part.
Oh, okay.
That is.
Yeah.
Is there ever a situation that we'd use reset over reset all?
So reset all resets the parameters and the variables. Reset only resets the variables. So reset would work as well. In this case, doesn't matter. You need parentheses. Okay. And so you also want to, so why is it not working? There are two things that need to be fixed. I'll let your classmates help you. Somebody? Can somebody help out?
I think
Are you're resetting after you set K?
Great, thank you.
Sorry, could you say that again?
You're resetting all of your values in M after you set K to the value that you want. So K is being
Oh, yeah,
reset.
that makes sense.
So why don't you try to do the reset all? Use reset all.
No, the syntax error is on the line above all.
Yes, you lost a parenthesis. And it's not a, it's lowercase l's for reset.
And the same on your last line there.
Okay, good. And now how can you get the two graphs on top of each other?
Use
Yeah.
M dot show after the last one.
Sorry.
M dot show open and close parentheses.
Okay. Do I need to put this inside that?
Oh no, you have a P instead of an O.
Yeah.
You need to do a show false on the in the plots. No. So in the plot, you need to say show equals false in the argument of the plot.
Got it.
Actually, you probably want to do the first one false and the second one true. That would be what you do. And then you don't have to do the second, the show at the end. All right. So let's see, why is that not doing what you want? Which one is it plotting?
The first one. No, the second one.
Okay. right. Well, for the moment, why don't we just live with having them separate? So why don't you just get rid of the show false and compare? Okay, so what do you see as different between the two? If we go back to what the questions were, one of the questions was, what was the time at which you reached the maximum number infected? So what happens when you make the duration of the eclipse phase or the latent phase longer?
The maximum number of infected is actually lower, and it takes longer to get there.
Does it change the total number infected at the end?
No.
No. Okay, good. Thank you very much, Delaney. Thank you, Ryan. Appreciate you willing to demo for us.
Sure.
All right. Okay.
I did a parameter scan.
Oh, great.
I
You want to
couldn't
show
figure
us?
out the.
Sorry, who was that? Was that Benjamin or Drew who was talking? Who was speaking? Who? Ben. Okay.
Yeah, sorry, that was me. Oh, yeah. So I didn't. I couldn't figure out how to get the times right. There was an error that I couldn't figure out. But for the final and the maximums amount of infected, I was plotting them on the from 1/2 to 1/28. It's weird. And then that's the change that I got. It might be so the for me the amount of final did change. I don't know if that's just because I didn't have a wide enough look at a wide enough scope, perhaps.
So I guess how long did you run the simulation for? 100?
100.
So why don't you run it for a longer period and see if that makes a difference?
Yep.
Because if you slow the eclipse phase to be very long, then the epidemic, as we saw with Ryan's demo and Delaney, takes longer, and so you have to run it for longer to get to the end. The reason you're seeing the jaggies in that orange line is because when you run for a long period of time, you need more points in your simulation. So if you make 1,000 there, then it should smooth things out. There you go. So that was good. That was good, great example, because it shows you that sometimes for the maximum number, you didn't have a problem. But for calculating that final percentage infected, it mattered. And so those are the kinds of things that aren't at all obvious when you're starting out. And it's important to sort of train yourself to look for those kinds of problems. That's great. Thank you very much for demoing. Is there anything else that people want to go over? Finding the max time we'll do maybe in the next exercise if you still want some help with it. Anybody else have something they'd like to show? That's great. We appreciate people being willing to go out on the limb and show their results. So another kind of model that we could do, I'm looking at the time because I want to make sure we get through the material today, was the idea of quarantine. Alternatively, this could simply be the period when you're sick enough that you're not going out and infecting other people. It seems to be the way that COVID works. In this case, you have an extra parameter, which is how long that quarantine phase lasts for. In the case of COVID, that would be about 14 days. 14 days. So that would mean mu would be about 1/14. And always, the parameters are rates, but it's often a lot easier to think in terms of the duration, so 1 over the rate. And so often, if I say 14 days, you have to remember that the rate constant is 1/14. And then the other thing is that presumably during the period you're at home, sick, you're not uninfectious, you're just interacting with fewer people. And so that alpha parameter means effectively how effectively you're isolated from the population. If alpha is 1, means you're identical to the I phase, which doesn't do anything. If alpha were 0, that would mean that you were completely isolated and infected nobody. In reality, that number is going to be somewhere between 0 and 1. Presumably, you could infect your family, but not other people if you're in bed, or infect people in the hospital, but not other people. And so that kind of model structure is something that one could play with. I think for today, we'll skip the exercise. It's very similar to the one we just did, but it does give you the opportunity to explore in more detail how these models work. In particular, as I mentioned, for COVID, effectively the people stay infectious in that I phase for about 4 days. If I fit a raw SIR model, I get the infectious phase lasts about 4 days, and that would mean mu was about 1/4. Lambda would be about 1/14. And that early uninfectious latent period could be 3 or 4 days. Now that's going to change as you change viruses. If you were doing influenza, you get different results. And so it's worth thinking about that. And I'm not going to ask you to do that right now, but it is important to think about limiting cases. If alpha were 0, we've mentioned, then I and Q are essentially identical. But in this case, we could also imagine what happens if remember that R naught is the number of contacts and their infectiousness, N gamma, divided by the recovery rate. In this case, that would be mu. And you might think about the differences. The total number infected depends only on R naught, but the timing of the infection will depend on N gamma and mu separately. So you might want to think about that. Something that you can do in a game like this is ask the question, what fraction of individuals were infected by the I people, and what fraction were infected by the Q people? And you could ask how that ratio changes as you change alpha, the degree of isolation. And that's a pretty important question when people are doing, when countries are doing quarantine. If you have a quarantine system where once you've been exposed, you're told to isolate at home for 2 weeks, you'd like to know whether that makes a difference to the total number infected or not. And it's actually quite an interesting question. How long do you have to quarantine for? And so a model of this kind can begin to answer that question. If the quarantine were perfect, alpha would be equal to 0. And then you could adjust the duration of the quarantine by changing lambda, the time you stay in quarantine, and see what happens. It's not an ideal model. How is alpha calculated? Good question. So alpha is a result essentially of the society. It depends on what alpha represents. If alpha is actually representing a physical quarantine, then it would depend on how effectively you are isolating the people who are quarantined. If you take quarantined individuals and you lock them in a hotel and don't let them out of their rooms, then that quarantine is probably pretty effective, and alpha is going to be very small. The fraction of people you infect during that quarantine period would be very small, and so alpha might be a few percent. On the other hand, if quarantine really represents the fact that when you're sick, you're staying home, you might still be interacting with your family and others, and then alpha might be more like a half, give or take. And so you have, but it's a very good question. Alpha is a result of either of a behavioral change. And so you have to find out what that is for a particular disease. In the case of a disease like COVID, we know that from the experience of countries like China and New Zealand and Australia, that strict quarantines where alpha really gets to be zero, near zero, are very effective. We also know that they're very hard to implement, and they're economically damaging and socially difficult. A disease where quarantine is used quite effectively as a containment strategy is Ebola. In the case of Ebola, because it's so lethal, and also because it's a bloodborne disease rather than airborne transmission, people first tend to obey the quarantine more, although not always, because there are outbreaks where people, in fact, escaped quarantine and then went on to infect large numbers of people. And because it's a bloodborne disease, it tends to be a little harder to transmit individual to individual. What you find with Ebola, which is different from COVID, is that people are still quite infectious after they've died. And so with Ebola, a lot of the transmission comes about because somebody dies of Ebola, they bleed profusely when they die, and when they're preparing the body for burial in a lot of traditional ceremonies, there's contact with the body, and so the risk of infection from the dead body is quite high. So that winds up being a problem. So normally in these models, once you're dead, you're dead. So there's a single dead category. And usually we don't think of the dead as infectious. But in an Ebola model, very often you'll have multiple death categories or multiple stages of death to represent the recently deceased and their interaction with the population. And then once they're buried, they're out of the system. So that was a great question, Alan. Okay, so again, the question here was if we quarantine people and the quarantine is very good, what happens to the times and final number infected? That's something that we should have people work on. But again, I don't think we want to do that today because I want to get through some more material, but that would be a good homework problem. As I've said before, one of the things that we do classically in this class is that if there's an exercise we don't do in class, we assign it as a homework. So you may expect to see that added to your little homework stack over the next week or so. And asking this question, what parameter regimes is quarantine effective and when not? And that could be both in terms of the value of alpha, but also in terms of the behavior of the disease itself. If the quarantine is short, it may not be effective. If alpha is near 1, it may not be effective. But you'd have to play and see what happens. Okay. But we've already seen a case where we did vaccination, where we got not steady state or saturating behavior, but oscillatory behavior. When we include births and deaths, and this was in one of the homework problems, but I think some people have done it and some have not. And this is typically not so much true of a disease like COVID that sweeps the population rapidly, but is true of diseases either they're seasonal like flu, or where the progress of the disease is slow, like hepatitis C or HIV, which is that in reality, the things that are affecting the population are not only whether you've been infected or not, but you also have deaths due to other causes. So you're removing individuals from the population due to old age and other diseases and accidents. And you also have births. And so even if you started out with a population that was 100% resistant to the disease, if you waited some amount of time, you would have new births. The births will not typically be immune, although there is maternal transmission of immunity for some diseases. There can also be maternal transmission of the disease. Somewhat surprisingly, it's not 100%. I'm always was surprised that with HIV, having a mother who was HIV positive didn't mean that the infant would be HIV positive. There's enough that even though there's a lot of sharing of blood between the mother and the infant, the fetus, there is a pretty good barrier keeping virus out. It's surprisingly effective, but there's some infection. But in general, you'd expect that the infants that enter the population or new immigrants would be would be susceptible. And you'll be getting rid of some of your R's by death. And so we started out with an SIR model. And what we did just now was add an E phase between S and I and a quarantine phase between I and R. Now we're going to add a birth phase. So we're going to have new births coming into our population. And we'll assume that S, I, and R individuals can all give birth. And we're going to assume there isn't maternal transmission of the virus from the mother to the child. So the new births will all come in the S phase. They won't come in as I or R. You could certainly elaborate on the model that way. And so we'll assume that there's some B, which is a birth rate, that's proportional to the total population. And of course, if we're trying to figure out births per day, that's a very small number. In the United States, the average woman will have during her lifetime about 2.1 children. So if you assume that a person lasts 80 years, the birth rate per day is 1/80 times 1/80 in parentheses now, 80 years times 365 days. So the birth rate would be on the order of 2.1 divided by 80 times 365. And women only represent half the population. So you have to divide by 2 again. So the birth rate would be 1/2 times 80 times 365. Clearly, that's a rate that's very small compared to everything else that's going on in the system. Similarly, if we assume you don't die of the disease directly, there's a death rate, a base death rate from old age and accidents. And again, that's also a small number. If you assume that the typical lifetime of an individual is about 80 years, again, that D rate will be about the same as the B rate. It would be 1 over 80 times 365. And so in one case, we had 2 divided by 2 times 80 times 365. And here we have 1 over 80 times 365. So actually B and D are almost equal to each other. If you were in a country with a high birth rate, like Pakistan, many African countries where you have typically 6 children per woman, then you would have B about 3 times the value of D. So why don't we try that? We're going to use a value of B and D that's much bigger than it really is. That is, let's try B equals D based on the argument we just had. It's assuming about 2 births per woman during her lifetime. But we'll make it faster. We'll make B and D equal to 0.01 per day, which is more like being a cat mother than a human mother. Because this is saying that each person is giving birth to a child every 100 days, which is silly. For cat, that's about right. Although the lifetime of the cat is longer. So why don't we just try that and run that simulation? So what I'd like people to do now is to take their base SIR model, add a birth term so that there's a source of S coming in, B times S plus I plus R, and have a death term where S, I, and R all die at the same rate. Is that a clear question? So why doesn't everybody try that to start out with and see how that goes? If you've gotten ahead of the exercise and your classmates, you might try making the birth rate more realistic by going to B equals D equals 0.001 and seeing what happens. You may have to run the simulation for longer. And then you might even try to make it really realistic and make it 1 over 80 times 365 and see what happens. Good question. How do you represent the death equations? Well, typically can anybody help? There you go. Somebody already, your classmates are a good source of information. An arrow pointing to nothing, just like in the picture. Try that out, see if that helps. But if you're done with the exercise, I'd say, again, I would try B equals D, the value of 0.01, which is people giving birth or dying every 100 days. Again, that would be maybe like mice or well, cats live a lot longer than that, but in terms of birth rate, about right. And then I tried 0.001. And then I actually tried something that was correct, where B is equal to D is both equal to 1 over 80 times 365. And the results are actually a little bit interesting for those 3 cases. So if you're still working on it, just focus on this particular case. But if you've finished that, you might try changing those time constants for B and D. And also, if you've done that, you might try changing the R naught value. Notice the R naught here is pretty big. R naught is N gamma divided by mu. So here N gamma is, let's see, n gamma is 0.5 divided by mu is divided by 1.1/5. So R naught's 2.5. If you wanted to try a different value of R naught, you could see what happens. In this case, the way you get to R naught matters. If you multiply n gamma by 2 and mu by 2, you have the same R naught, but it's a slower disease, and you'll get a different result. You could try that also if you haven't, if you have already finished the rest of the exercise. People shouldn't be shy about asking for help. If we were all in the classroom, we'd be doing that. So no reason we can't do it here. Okay.
This is what I have right now. I don't know how correct it is, but I tried to do the thing you said with the death rate, and then I added this in for the birth rate, I guess.
Okay. So let's look at the birth rate equation first. Does anybody see what's an issue with the birth rate?
No. That's what it is.
Okay, good. There we go. Okay, that's good. And what about the death rate? Somebody have a comment on the death rate equation?
D times R.
Right, you don't have the rate, Ellie.
Oh. What would I put for that? For like, would it be here or?
Would it be D times R?
D times R is the death rate.
So
So
like,
what will that do? So Ali, you tell me, what do you think? What would that do, what you just wrote? What's the
take the fraction of the people dying and multiply it by the people that have recovered? I guess.
Well, there's a formal way to convert the diagram into a statement. Where does the rate go in your rate law? So why don't you look at line 6, for example, equation 2.
Oh.
Yeah. Okay. Okay. So why don't you see what that does? See if that does something.
Yeah, see, I keep getting this, but I can try to restart my terminal.
No, that's not a syntax error. So let's take a look at your code again. See why it would be doing that. It's
There's
crashing
one-
on the load, so it's not parsing the load properly.
There's a semicolon missing with the mu. I'm not
Yes.
sure.
I tried that, I think, and it didn't. Yeah, it still didn't.
Yep.
So there definitely is a typo in one line. You could put a semicolon after like line 4, although I don't think that's where it is.
I'm not sure if things like line 13 are allowed in Tellurium.
Yeah, I was going to say that.
Oh, okay.
But maybe I'm wrong. I really don't know.
I mean, I can try it. Yeah, that worked.
Okay. And there's one other thing which may or may not be significant, which is in our original model, the S and the I populations also die. So you would have equations that look like line 7 for S and I as well as for R.
Okay.
So you could copy line 7 and then turn the R's into S and the I into S and the R into I. You have to give it a new number. The order of the lines doesn't matter. So you can just put it at the end if you want.
So I do that after like each of these.
You could, again, the order of the lines doesn't matter. This isn't like a standard program. But you do have to give them unique numbers. So you could have your S's going away, or I's going away. Okay. Your S,
Like that, and then the same for R.
right, and then the same for R. I mean, sorry, you've got I for I. Okay. And then there's one other thing that maybe is a little counterintuitive, which is in line 4. You're not converting B into anything. Your birth rates are coming from out of the air. And so there's nothing there. Okay, there you go. Okay, great. Let's try that. All right. So now we probably have to run it a little bit longer because we're only running 50 days. And even if people are reproducing over a period of 100 days, that's still too short. So you have to run it over a longer period of time. So why don't you run it for 2 years or 3 years?
Can I say like 1,000 days or?
That would be fine. You're going to have to change the number of points probably to make it longer.
Oh.
So 100 points, you probably want 1,000 points. Okay, good. So you're seeing something that you already saw in your vaccination model. S goes to S at a rate times S. Well, what you'd want to make, let's make the birth rate more realistic. We'll do that in a second. This is fine. So what you see is these oscillations. You see waves of the epidemic, which we saw in the vaccination model. Okay. And so now let's make the birth rate smaller. So we'll make B 0.01 instead of 0.001 instead of 0.01. That would be you give birth every 3 years. It's still much too fast, but all right. Okay, and now you see you're stretched out the oscillation. And this is getting sort of interesting because this means that the epidemic comes back every how often? What's the interval between your peaks and your epidemic?
Like 900 days or?
900 days, so about every 3 years. Again, you could run for a longer period of time. You could run for 10,000 days, so 30 years. So why don't you make it run for 10,000 days? And again, you'll have to add one. And you see you get these peaks. They're not quite equally spaced, but they're every couple of years. And so this might be surprising to people. In other words, you might say, you expect an epidemic like flu that comes back every year, but why would you have an epidemic that comes back every several years? Why does it go away for 5 years and then come back? And so that could be because of the low birth rate, death rate. Notice the amplitude of the oscillations is pretty big. Let's try doing it with realistic birth rate. So let's make the birth rate 1 over 80 times 365. You'll need parentheses in the denominator. 80 times 365. Have to have parentheses around the denominator only. No, that won't work. You want to divide by 80 years and days.
Oh,
Okay, let's try that. Let's see. Is that a, okay, so now we have long oscillations. And now we have to go to even longer time. What would happen? So,
you want me to increase the time again?
it's too many. Okay, so here we have a long period. I think that something doesn't look right in this. Let's take a look at the simulation a little bit. Something maybe did we make a mistake somewhere? N times gamma infection last 5 days. This looks all right. So I believe your result. You get a huge infection early on, then the infection goes away for years, and then it comes back and you get those pulses. Did anybody else get something similar to that? Something different from that? No, yes. But thank you, Ali, for doing that. That's great. That's very helpful. Does anybody else want to share some results? This was my result when I did the realistic birth and death rate. And so let's see, 20,000, 1,000 is 3 years. So we're getting the disease coming back every 60 years, which is something that might seem like a new disease to people, right? You have a pulse of the disease here at the beginning, and then essentially no disease for 60 years, and then it comes back. And that might be surprising to people. You'd say, if the disease went away, why did it ever come back? And that could be because of the loss of infection due to births over a long period of time. So in a sense, that's rather an interesting result, that you can get that the realistic rates of births and deaths mean that you can get diseases that go away for long times and then seem to come back and sweep the population, apparently without warning. So now, in principle, there's a lot more we could do. There's a lot more we could do with the epidemiological modeling, but we're going to be focusing now on doing the, let me see what happened in screen share. So we're going to be focusing for now on the case of in-host modeling. And to begin with, we're going to get models that look just like our SIR models. So we're going to say, why did we bother to make the change? And the reason we're going to make the change is because even though the base model is going to look very similar, when we start dealing with in-host models, we have an immune response, and that's going to change our results. So if we look at the viral load in an individual, how much virus you have circulating in your body as a function of time, we find out that the time course of the amount of virus in your body changes in different ways for different viruses. There are viruses where the amount of virus goes up. It's called monophasic decay. It goes up, reaches a maximum, and then goes down almost like a parabola to zero. And that is not a terrible, well, there are viruses that do that. The second one is one where the amount of virus goes up very steeply. It reaches a maximum. There's a period of slow decay of the virus and then a later period of faster decay. In some cases, you have a situation where the amount of virus goes up. It initially decays rapidly, then decays more slowly and eventually clears. And there also are viruses where it goes up rapidly, goes down, and then stays at some non-zero level for a long time or maybe forever. An example of that last one might be herpes or HIV, which your body doesn't clear entirely. This triphasic decay where you have the peak and then the slower clearance could be a situation where you have the virus getting into an organ system where it's easily cleared, and then, for example, crossing the blood-brain barrier into a tissue that's harder to get the virus out of. When the virus is cleared completely, we say that the disease was an acute disease. When the virus sticks around forever, or at least for a very long time, we say it's a chronic disease. And if we look here in vitro, and so these are in cell cultures for COVID, this was done very early on for COVID in a variety of different cell types. Some of those cell types were compatible with COVID and not. What we see is, so here there's no immune response, at least no cellular immune response. There's still interferon immune response. What we see here is first they only sampled the virus every 6 hours. They didn't sample it very high frequency. And so for the first 6 hours, they saw essentially no virus in their dishes. Then they saw quite a rapid rate of increase. Notice it's a log scale on the y-axis. So each one of these ticks represents a factor of 10 increase. So between 0 and 6 hours, they saw no increase of virus. Between 6 hours and 12 hours, they saw 3.5. They saw approximately a 3,000-fold increase in the amount of virus. Then between 12 hours and 18 hours, the amount of virus continued to go up, but at a much slower rate, about not even a 10-fold, about a 5-fold increase over the following 6 hours. So you had a 6-hour period when the virus increased by a factor of 3,000. And then over the next 6 hours, it increases by a factor of 5. And then depending on the particular cell type they were looking at, and whether they were looking at the virus in the cells or in the solution around the cells, they got a different result. In these Vero cells, one kind of cell that's used in cell culture, the amount of virus kept going up until 36 hours post-infection and then saturated. The black line indicates the virus inside the cells. The dashed line indicates virus that the cells secreted into their environment. And you also see, if you look between the solid black line and the dashed black line, that there's a delay of about 6 hours. So the cells start producing virus after 6 hours, but they only start releasing virus into the outside world after 12 hours. In the case of these green lines, that's a different HUH7 cell line, different cell line. It obviously isn't as compatible with the COVID as the Vero cells were. The cells started out making virus about the same time, the solid green line, but they didn't start releasing it into the solution around the cells until about 30 hours. And the total amount produced saturates here at 3. The other one saturated around 6. So that's a factor of 10 to the 3, 1,000. So the black cells, these Vero cells, produced about 1,000 times more virus than these green HUH cells. So that tells you that the cells, that the virus is able to get into certain kinds of cells and not into others. And we now know that that depends on this ACE2, primarily on this ACE2 receptor density for the cells. And so already, and this paper was published very early on, I think in April or May of 2020, quite early, there was already evidence that there was a big variety of cell responses to COVID. If we look at a simple model of what's happening, we have an idea of susceptible cells. The susceptible cells, here called T instead of S, can become infected. In this basic model, we are going to assume that there are latent, that eclipse phase, that SEIR type model. The E's tend to be called I1, early infected cells, in host models. So we have to be used to the fact that the naming is a little bit different. After this eclipse phase, the cells begin to secrete virus, release virus into their environment. And so we have virus in the environment, and that can go on and infect new cells. In principle, the susceptible cells can reproduce just the way we did in our SEIR model or BDSIR model. And so we have a very similar result to the one that we had before. We can build all sorts of network models of viral infection inside your body. As I mentioned, there are complexities in your body because you have an immune response. In our simulations of epidemics, we didn't have the complexity of the immune system to deal with. There's a very famous mathematical biologist named Alan Perlson, who's done a lot of epidemiological models. He also has done a lot of in-host models. Alan is at Los Alamos National Labs. He tends to like to do very simple structured models. His models tend to look very much like SEIR models. There also have been models trying to ask the question, what happens when you have two viruses at the same time, or what happens when you have a virus and a bacterium at the same time? This was a model by Perlson and Smith, which looked at what happens when you have both bacterial infection and viral infection at the same time. That might seem like an academic study, but in lung infections, it's pretty common to have both a bacterial infection and a viral infection at once. That's why when you go to a doctor with a cough, even if the doctor says that you have a viral infection, they may give you an antibiotic. The antibiotic isn't to try to do anything for the virus. The antibiotic doesn't work on viruses. But it winds up that in certain cases, if you have a viral infection combined with a bacterial infection, the consequences are much worse. And so they'll give you the antibiotic to try to knock out a bacterial infection. In particular, if you have pneumonia from the viral infection, so you have fluid accumulation in your lungs, then bacteria sometimes can thrive in the fluid, and so you can get a secondary bacterial infection. This is a model on top. It's a more complicated model, which is actually trying to model the details of the immune system. In this case, the various boxes here represent both the inflammatory response, the lymph nodes, and the systemic immune response, and the local in-tissue response. There are a whole variety of cell types involved in the immune system. Natural killer cells, macrophages, neutrophils, CD4 plus T cells, CD8 plus T cells, and a bunch of other ones, each one of which plays a specific role. In addition, there are a lot of chemical species that are important. Early on in infection, interferons are important. They send signals from cell to cell to prepare for viral onslaught. In the intermediate stages of viral infection, you have interleukins. Interleukins 2 and 6 are particularly important in the early stages of cellular response to viruses. IL-2 and 6 are the things that give you a fever and a headache. Later on, there are interleukins that are associated with recruiting immune cells. So these are now cytokines to chemokines, and cytokines to recruit immune cells from the lymphatic system into the infected tissue. And then later on, there are interleukins that will turn off or damp down the immune response. And then still later during the course of the disease, typically after 10 to 14 days, your body will start producing antibodies. And those antibodies will act both by binding directly to the virus and also by stimulating the cells to resist the virus or killing the cells that are infected. So there are a whole series of immune responses that one could model. Let's start out by looking at some experimental data that was published by Smith for influenza. This is influenza in mice, so now not in a dish, but in animals. There are a couple of issues with these data sets. The first one is that actually measuring the amount of virus in an organism is not so easy. It seems that measuring the amount of virus in an organism should be easy. You take a swab of the throat, you take a swab of the nasal passage, you take a blood sample. And in principle, you could use a cell sorter to count how many virus particles there are. You could look in an electron microscope and count how many virus particles there are. One problem with that is you have to standardize the volume you're starting with, because you need to know density of viral particles, and that may depend on where the sample is taken. The other thing is that viruses are not very good at making themselves. And so a large fraction of the virus particles for some viruses are not actually able to infect. An easier way to do the measurement is to do qPCR, quantitative PCR, which looks at the RNA or DNA of the virus. And again, the problem is that you have a lot of more viral genome than you actually have viral particles, and the genome by itself can't infect. And you might say, well, there must be some number that converts the number of virions into the number of infectious virions, or the number of RNAs into the number of infectious viral virions. But those numbers and the estimates of them often differ by a factor of 10 or 100. And so it's not so easy. The easy measurements to make, which count the genome directly, don't tell you how many infectious virus particles you have. And so the classic experiment to do is to take a swab, for example, from your nose, to dilute the liquid in that swab, to put it onto tissue culture plates, and to see either what dilution has 50% of the culture plates show infection, or whether 50% of the cells in the tissue culture are killed. And that means doing serial dilutions and then individual experiments where you look at how many cells died in the culture. And those are very expensive, time-consuming experiments to do. And they're also not very accurate. And so the result of that is that people tend to make measurements of viral load only infrequently, typically once per day or less in humans. And the estimates of the viral load are given in this funny unit, TCID 50, which is the dose that's required to get half of the cells or half of the cultures to die. And that the estimates are not very accurate. So with all of that said, this is an experiment that's not so easy. In addition, mice don't get influenza very easily. And so to get your mice to get flu, you have to work at it. And so that may not be quite representative of what happens in humans that get flu more easily. But here we are. This is the data set we're going to look at. So we have a measurement at a time that's not quite 0. We see relatively rapid, again, this is, remember, a log scale on the y-axis. So 0 to 4 is a 10,000-fold change in the viral load. So from 0 to day 1, we see a 10,000-fold increase in the amount of virus. Then sometime between day 1 and 2, there is something that comes close to being a maximum, saturation. Maybe day 3 is a little higher than day 2, although that's not always so easy to tell. Then we see a period of 1, 2, 3, 4, 5, 6 days, during which the amount of virus decreases slowly. And then starting from day 7, we see a rapid decrease in the amount of virus until effectively there's no virus left at days 9 and 10. So we see a pattern of a delay. Exactly how much delay we can't tell from this because it's less than a day, so we don't have temporal resolution. A period of a day or 2, day and a half, when the amount of virus increases very, very rapidly. A maximum around day 2, maybe day 2.5. And then from days 2 down to day 7, slow decrease of the amount of virus, rapid decrease of virus around day 7, day 8, day 9, and then essentially no virus thereafter. I'll call your attention in particular to day 8, where there were some individuals where the reading was 10 to the 4th, 10,000. And there were other individuals where the reading was 0, 1, which is 1, when you put it on the log scale. And so there's a 10,000-fold uncertainty in the amount of virus on day 8. And so you have to take that uncertainty into account when you're thinking about understanding these experimental measurements. Are there any questions about that so far? Because this is really pretty important to be able to think about how to look at these experiments. So the initial lag phase, which we don't really see in this picture very well, maybe 6 hours of it, corresponds to the time it takes from the virus to get into the cells to the time the cells start producing and releasing virus. Then we see a period, this rapid exponential growth, when those infected cells are releasing virus into the medium and infecting other cells. Then we see this slower period here labeled 4, when we see what's called the innate immune response kicking in. That's interferon, macrophages, and natural killer cells acting. And then once the adaptive immune cells, that would be both antibodies and CD8 plus T cells, come in, we get rid of the virus very quickly. So what we're going to do, and this was that homework problem that was probably pretty mysterious. It was homework problem number 3 that got assigned early, was to try to get an estimate of the timescales for what these different phases of the virus. And your homework assignment was to pick a different virus with a different curve and try to get the same kind of observations. And what you really want to do is represent the phases of the viral infection. Here they're labeled 1, 2, 3, 4, 5. And for each phase of the infection, you want to get a sense of the rate, the duration, and the value. And so the first thing that we're going to see here is the eclipse phase. And if we look at the line that's been drawn to guide the eye, it's not really a measured line, we see that there is a gap of about a quarter of a day during which nothing happens. And so we're going to say that there's an eclipse phase when there isn't any viral production, about 6 hours. So once virus gets into the tissue, it takes 6 hours before any new virus is produced. That's actually a number that's hard to estimate. We saw it better in that in vitro study of COVID, where we actually saw that number pretty well. The next thing we have to estimate is this exponential phase. And that goes from a time of about a quarter of a day up till about a day and a quarter. And we start out with a value of 10 to the 0, 1. We wind up with a central value of around 10 to the 4th. So that means that we actually go up. Actually, I drew my line wrong. To get to a day and a quarter, we would have to go to this a little bit further, up to about where this red line is intersecting that black line there. And that's more like 10 to the 6th. So we get an increase of 10 to the 6th over 1 day. That's about tenfold over 4 hours. And so that means that our rate of increase is about 1/6 per day for about a day, lasts about a day. And the maximum value here is about 10 to the 6th at a day 1 1/4. So now we have a delay of a quarter of a day at a value of 0. We have an exponential growth of tenfold over 1/6 of a day that lasts for another day and gets us up to a value of 10 to the 6th. And now during this longer period of time, we have a decrease from about 6 to about 5. So we have a tenfold decrease. And how long does it take? It takes 1 day, 2 days, 3 days, 4 days, 5 days. So we have a tenfold decrease over 5 days. Remember, we had a 1,000-fold increase over 1 day. Now we have a tenfold decrease over 5 days. And then in the tail of our experiment, it's a little bit hard to know what to do with day 8. In this case, I'd assume that the real value was 0 at the end of day 8. And that takes 2 days. And so I have a decrease of 10 to the 5th over 2 days. So that is tenfold change over 2/5 of a day going down. And there was a question, is eclipse phase synonymous with lag phase? Good point, good question. There is a certain amount of inconsistency in the way names are used. And so you'll see eclipse phase and lag phase used more or less interchangeably in literature. The reason, and in the case of the SEIR models, E could stand for eclipse or it could stand for exposed. So you'll see some ambiguity there as well. But now we have our phases: eclipse phase, exponential growth, saturation, slow clearance, and rapid clearance. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We have a rate or a duration of these. I've really mixed things together because I've got a duration for the eclipse phase, and I've got a rate for the others, and the value for the saturation phase. So I really should have made a table which had more columns in it, but then it wouldn't have fit on my picture. So this was the task that homework problem 3 was trying to assign to you. And as I said in my email, I realized it wouldn't make a lot of sense until we had had this discussion. So is it clear how to look at a diagram like this and what to do with it? Because this is a very fundamental thing that you need to do if you're going to look at modeling a new virus, or to understand how the parameters were determined for a virus. You're going to have to know how to look at a diagram like this. And so feel free if you have any questions to ask them, because it's not a trivial thing to do, to walk through these different steps. These parameters then we're going to use again and again as we try to build a model of what's happening with this virus. So now we're going to try to build a little model of in-host viral infection. Given the time, we're not going to get through all of it, but we can get started. And we want to understand the very minimal things that we need to be able to explain that curve. And so what we want to do is we're first going to identify what the variables are and how they're transitions. That's going to be like writing the arrow diagram. S goes to I, goes to R before. We're going to build it one at a time, starting from the earliest time in our simulation. And what we're going to do is we're going to try to fit successively the lag phase, the exponential growth phase, the saturation, the slow decay, and then finally the fast decay. And what we're going to find out is that doing the lag phase is easy, the exponential growth is easy, the saturation is easy, the slow decay is easy. And then when we come to actually trying to fit that tail where we get the fast decay, we're going to have more difficulty. And the reason for that is that biologically, the processes that are at work get more and more complex as we go to the right, as we go later in the viral infection. So to begin with, we're just going to think about infection and viral replication, and we'll talk a little bit about biology and a little bit about math. So these are some slides that were generated a year and a half ago, a little more than a year and a half ago, 18 months ago. No, a little more than a year and a half ago, by a student in the spring version of this class, Sam Heaps, who went on, based on this work, to be a consultant, building computational models. He works for consultancy now. And he gave a very nice lecture on the biology of viral infection, because he came from a biology background, not mathematical or engineering background. And he generously allowed me to share his slides. So one of the things that has to happen to get infected is that your body actually is pretty good at keeping viruses out. And once they get in, it's pretty good at addressing them. When you get an infection, the virus has to have gotten over a series of barriers. And typically, we're going to start our clock when the first cell in your body gets infected. In fact, the there are what are called barrier functions, which keep viruses and bacteria out. And those barrier functions are different in different organs. Your skin is a classic barrier function. Your lungs have mucus, which is a barrier function. The hairs in your, both the macroscopic hairs, say in the nose, keep out extraneous particles. Your nose has turbinates that filter air and direct particles into particular regions that are protected to some extent. And you also have the transport of mucus in your lungs from lower in your respiratory system up, so that any virus that gets down deep in your lungs tends to get transported up and eventually expelled in the form of a cough, which is great from your point of view, but not so good if somebody is coughing on you. And so there are a variety of barrier functions. Some of those barrier functions are physical, like the ones I've just described. Some of them are chemical. So your skin has a lot of RNA aces, which are molecules that break down RNA. And the reason that you have in your skin molecules that break down RNA, they break it down very effectively. So when you work in a lab, you have to be very careful not to get sweat into your test tubes. If you're working with RNA, is that many viruses, like coronaviruses, have a genome that's encoded in RNA. And so those chemicals basically are chemically attacking and breaking down the virus. If the virus gets into your body, there's what's labeled here the intrinsic immune system. That would be complement in the blood, which are molecules that bind to viruses sort of generically. Molecules like RNases that break it down, but break viral genome down. And also responses like interferon, which we'll talk about probably a little bit, not today. We'll talk about a little bit today, but more later in the class. And then you have other kinds of immunity coming later. When we think about viral infection, we first have to have the virus get into our cells. So here we have a picture of some kind of epithelium. Those could be in the lungs. So these are cells in the lungs. You see the virus binding to the top surfaces of those cells. This could be the lining of the gut too, or the skin. Once the viruses have entered the cells, that they're going to begin to reproduce, the cells themselves, once they're infected, will send signals called cytokines that are telling immune cells that there's an infection. Those immune cells will then go to the lymph nodes and send signals to trigger the adaptive immune system. And eventually, the immune system, the lymph nodes, will send back to the tissue a targeted immune cells and also antibodies. When we look at the process of viral infection in a single cell, viral replication and release of the virus, there are a lot of steps that have to be gone through. That's one of the reasons that there's this latency, this eclipse phase or lag phase. This was a famous poster that was produced by a company, antibodiesonline.com, and it was talking about possible ways of attacking COVID, SARS-CoV-2 virus, during different phases of its life cycle. First, to get into a cell to reproduce, the virus has to get into the cell. And there are different ways that it could do that. SARS-CoV-2 can bind to the ACE2 receptor. That's not a receptor that is there specifically for the purpose of getting virus into the cell. It's a receptor that cells, in particular in the blood, in the vascular system, used to regulate blood pressure. But it unfortunately happens to bind to the spike protein on the viral coat. When the virus binds to ACE2, it creates what's called an endosome, a region of membrane that surrounds the virus. It's pulled into the cytoplasm, and then that virus itself will disassemble and release the viral genome into the cytoplasm of the cell. That DNA, that's the RNA in this case, for the virus, is then copied by an RNA-dependent RNA polymerase, which makes multiple copies of the RNA. Some of those RNAs are then cut into pieces, given to ribosomes, which transfer the genomic information of the virus into proteins. Once those proteins are made, intact copies of the viral genome are combined with those proteins to make new viral particles, new virions. Those virions then are put through the Golgi apparatus, put back into endosomes, and then released from the surface of the cell. The release itself requires particular proteins to cleave the virus off of the surface of the cell. And if you look in specifically SARS-CoV-2 in electron micrographs, you'll see that there are lots and lots of virus particles that stay stuck to the surface of lung cells. They never get separated. And if they don't separate, they can't go on to infect other cells. And there were some estimates early on that only 1 in 30 or even 1 in 100 of the virus particles that were manufactured by the cell actually get out into the world and can infect other cells. So there's this complicated life cycle of the virus. First, the virus has to attach to the surface of the cell. It has to be brought inside of the cell. There actually is another way that the genome of the virus can get into the cell, using a second receptor, TMPRSS2. In that case, perhaps the viral genome was injected directly into the cytoplasm, although it's not obvious that that's the case these days. So the virus has to get first attached to the surface of the cell. Secondly, be pulled into the cell. Thirdly, the coat of the virus has to be disassembled, and the viral genome has to be released into the cytoplasm. Once the viral genome is released, the RNA-dependent RNA polymerase, which has to be provided by the virus itself, has to copy the viral genome. And this is an important step. In fact, this is the critical step where the viral genome is copied, because that provides exponential amplification of the number of viruses. Then the genome itself has to decide whether it's going to be cut up in pieces and used as a template to make proteins, or it's going to be preserved and used to make new virus particles. Then those pieces that are cut up have to be translated from RNA into protein by ribosomes. The proteins have to assemble along with the genome. That has to be transported to the membrane, and then it has to be cleaved. So there are lots of steps. And there were attempts early on in SARS-CoV-2 history to block all of these different steps. The one that wound up being approved for use was remdesivir. Remdesivir blocks this genomic replication by interfering with the RNA-dependent RNA polymerase. But if you look at some of the other drugs that have been tried and failed, like ivermectin, they address other stages of the viral replication. For the moment, we're going to neglect a lot of that complexity, but there are pieces of it that we have to model. And the first thing that we have to do is we're going to have a population. This is our SI part of our population model. We're going to have a population of uninfected cells. Imagine the cells in the lining of the throat or the nose or the lungs. These are cells that have a receptor for the virus, in this case ACE2. And that means that when there is virus present in the environment, they're going to bind the virus and become infected. And they're going to not yet be producing virus, they're going to be pulling the virus in. Once the virus has entered the cell, it's definitively infected. And in general, the only way a cell can be eliminated from your body that has virus in it is for the cell to die. In some animals, in particular bats, which are the host species, they seem to be able to actually turn the virus off in infected cells. But in us, once a virus has entered a cell, the only way for your body to get rid of it is to kill the cell. And so we're going to have our classic SI model. We're going to say that if we have an uninfected cell, the probability that it's infected is proportional to the amount of virus in the system, V, times some infectivity beta. And if we wanted to be fancy, that beta would depend on the amount of ACE2, the amount of receptor on the surface of the cell. And so the transition from uninfected to early infected cells, or eclipse phase cells, looks like the equation we used before. T goes to I1 at a rate beta times T times V. So increase the amount of virus, increase the rate of infection, increase beta, increase the rate of infection. Now, in reality, when a virus particle interacts with a cell, it enters the cell. It's not available to infect other cells. And so we should really be writing this as a chemical reaction, which is T plus V goes to I1. So the virus is used up. The problem is that the units that we measure virus in are these colony forming, these plaque forming units, these TCIDs. And we don't know what fraction of the viral particles in the environment are used up during the process of infection. Clinically and experimentally, it looks like the fraction of virus that's used up is very small, but it's not zero. And we can explore the consequences of that in exercises. Typically, when you see this written out, you'll see an equation that looks like T goes to I1 at a rate beta times T times V. And this is something that we discussed in the context of infection in epidemiology. If you're an uninfected individual, what matters is the probability that the people you meet are infected, which is the total number of infected people divided by the total population. Similarly, in this case, V usually represents the total amount of virus in the system, but what you care about is the amount of virus that you as an individual cell are encountering. And so we should be dividing the amount of virus by the number of by the initial number of uninfected cells. That gives us the amount of virus per cell. And since we have to keep the equation the same, that means beta gets multiplied by the number of cells. And so beta times T0, the initial number of uninfected cells, is the rate of conversion from uninfected to infected per unit virus per cell. And again, dividing and multiplying by the same thing doesn't change the final result, but the units of the parameters are different. And it winds up, this is actually an issue because when you write it this way, beta times T times V, where V is the total amount of virus and beta is the infection rate given the total amount of virus and the total number of cells. If you change, for example, the size of the tissue patch you're modeling, this equation changes in an unpleasant way. This one doesn't. And so it's important to actually write the equations right. And you'll find if you're trying to replicate papers and look at other people's results, that very often they don't write the equations right. They write them this way, and then you have to interpret the parameters. If the amount of virus is constant, then this gives you that the number of uninfected cells is T0, the initial number, times e to the minus beta Vt. So you have an exponentially decaying number of uninfected cells. Or equally, the number of infected cells is going up exponentially. And so what this is telling you is that the slope of that exponential growth curve in our experimental data is just beta times V. And so I think we're going to run out of time. Next week, again, we're going to do paper replication with Giuliano, and Giuliano will show you how to upload simulations to NanoHub. I hope I can join you. If I can, I will. If not, I will be seeing you in 2 weeks. And so I hope now, for the purposes of that homework problem 3, we've walked you through it. And we're going to start now next time that we're all together. We're going to start building a simulation of in-host viral replication line by line here. You may very well go through a lot of this when you're doing the paper replication, because many of the papers that we've considered for replication will have this in-host model in them. So I hope that gives you a place to start. So before we break, are there any questions before we stop for tonight?
Can you go back to the last slide really quick?
This one?
Yeah, thanks.
Okay. What can I help with? What would you like to say?
Oh, I just didn't copy the whole equation down.
Okay. All of the slide decks are available to you. I mean, I certainly encourage you to take notes or take screenshots. That's fine. But all of the slide decks are in the student material folders. So if something goes by too fast, the videos are available, although sometimes it takes me a little while to trim them to make them more accessible. And the slide decks are saved. So sometimes it takes me a little while to get the edited slide decks into the student materials folders, because once I see that, I don't always know exactly where I'll finish, and I also will sometimes catch errors in the slide decks, which I'll fix. But you should have access to the slide decks. If you don't have access to a slide deck, let me know, and I'll make sure that those get uploaded.
Okay,
But absolutely, please feel free to take a look. Okay, any other questions or comments before we break? No. Well, thank you very much. Appreciate everybody sticking around tonight. And I will look forward to hearing from you during the next week, and talking to people if they have questions. And I may see you in a week. If not, I will see you in 2 weeks. And Giuliano, you'll be in good hands with Giuliano next week and teaching. Okay, thank you, everybody. Appreciate your being here. Good night.
Thank you.
Thank you.
Thank you.